once a graduate student at UC himself, earning his doctorate under the late and great Nicolac Jr. He grew his fame in the semiconductor field through the discovery of 3-5 oxidation, and after over 20 years in the optoelectronics industry, returned home to academia. He is now a full professor in electrical engineering and holds the titles of VP Strategic Development at Electron Devices Society, and is the editor-in-chief at the IEEE Journal of Quantum Electronics. And without further ado, please join me in welcoming Professor John Dallesasse.
Thank you. I want to encourage everyone, to just ask questions anytime throughout. I mean, I knew that this kind of the forum is a good one for more, discussion and exchange. So again, please jump in as I'm talking here. I don't know, we'll get through all my slides. It's a fairly comprehensive overview of some of the things that have gone on in heterogeneous integration, but again, hopefully everyone finds it beneficial. When you talk about heterogeneous integration, it kind of reminds me of the, and I'm not sure who you can attribute it to originally, that it's an overnight success, 20 years in the making. In recent years, you've seen a lot of dialogue about heterogeneous integration, ways to bring non-silicon semiconductors onto the silicon platform. In fact, at the recent Microelectronics Commons annual meeting, which was talking about, the EMI Commons, for those of you who aren't aware, is one of the first tranches of CHIPS Act funding coming through that's more DoD related. But everyone who was presenting was talking about heterogeneous integration as a methodology for enhancing the performance of silicon. This is something that has its roots that really go, way back, to even the early days of epitaxy, of compound semiconductor epitaxy. So I'll walk through some of that. So just a couple things I wanted to discuss. First of all, what are some of the emerging applications? Why do we need to contemplate bringing non-silicon semiconductors onto a silicon platform? What sorts of functions can we bring, as we bring those materials onto silicon, is another key consideration. What progress has been made for some of the key applications over time. And then, I'll talk a little more about photonic devices, which are my personal interest area. And then maybe a few comments on what sorts of things are next for photonic integration. And then just as a little bit of background, this is adapted from a plenary talk I was asked to give in Taiwan that was related to heterogeneous integration of materials. So this is not my work in a lot of cases, but it kind of summarizes things that have been done over time by a number of different people. And then I've got a little bit of a section where we're talking about some of the things we're doing here at Illinois as well. But it was really put together to give a more comprehensive overview of the sorts of things that have happened over time. So the first thing is, what do we want to do? What do we want to bring onto a silicon platform? And of course, the other question is, why do we want to bother with silicon? Well, of course, it's hard to argue with people that make 300 millimeter wafers, right? Silicon wafers are massive. The infrastructure for producing silicon devices, has been developed over, millions of person years of effort, right? And anyone who says they're going to displace silicon is probably, a little bit overconfident, right? You're not going to displace silicon. Silicon does certain things incredibly well, but it also has limitations, and trying to augment its functionality by overcoming those limitations is where heterogeneous integration comes in. Okay? So, we'd like to be able to take the sorts of large-scale integrated devices you can make on silicon, and add other things to those. You know, we'd like, for example, to be able to do photon generation and control. You know, we want to be able to detect photons, so we can basically augment silicon by adding photonic functionality. People are talking about quantum devices. You know, can we enhance silicon, you know, by bringing various devices that are being used in quantum information, quantum communications onto that platform as well. You know, if we start talking about, you know, things like, you know, like AI systems and other sorts of things, you know, are there other kinds of devices, you know, for example, you know, magnetic devices, you know, or other sorts of non-silicon devices that can be used for those sorts of things. You know, of course, you know, beyond just the conventional electronics, there's an interest in pushing the speed higher. So does it make sense, you know, to augment silicon with materials that can run at higher speed? You know, so you basically have CMOS processors, and maybe at the edge of those devices you have things like high-speed electrical multiplexers and demultiplexers that are implemented in other materials that enable you to push, you know, a little bit faster. Okay, you know, turn up to 11, right? And then bio-inspired materials, right? I mean, people are looking at biological systems. You know, is there something in the future that involves augmenting silicon by having something, you know, of a biological nature? And when we think about incorporating functionality of some kind, you know, what would be ideal is that if that were an actual layer in the CMOS stack, right? So we start by taking our wafer coming out of the front end of line process. We incorporate one or multiple layers that have some sort of additional functionality, 3-5 materials, etc. And then we basically build the rest of the stack on top of that. So we put all of our interconnect layers and everything, so that effectively what this becomes is an augmented integrated circuit that has this enhanced functionality embedded in it. Okay, and this is obviously where we'd like to be able to go with this eventually. And I mean, just, you know, stepping back again and saying, you know, from a silicon perspective, what does it do well? What does it do poorly? Well, I mean, from the standpoint of things it does right, again, you can't argue with the manufacturing infrastructure, right? I mean, you know, we have, it costs $20 billion to build a fab. There's fabs all over the world. You're not going to replace that infrastructure with something else. And it's a, you know, so to speak, well-oiled machine. Silicon is robust. You know, if you work with silicon versus 3-5 materials, and how many of you handle 3-5s regularly? Probably at least a handful of you, right? Okay. If I have a silicon wafer, you know, and I'm holding it with tweezers and I drop it from here, it's probably going to bounce, okay? Maybe it'll break, but it'll probably bounce, okay? If I do the same thing with gallium arsenide, it's going to break, right? If I do the same thing with indium phosphide, it's going to break even worse. You know, the fragility of the compound semiconductors is difficult to deal with when you talk about scaling up your processes. And, you know, that's one among many reasons why you haven't seen the same scaling in 3-5s as you've seen in silicon. It's easy to dope, different types, P-type, N-type. You know, obviously CMOS itself is powerful, very low static power dissipation. That's one of its advantages. From an optical perspective, silicon is great for making waveguides if your wavelength is above about 1.1 microns, right? Below that, it's not good, it's opaque, right? And of course, one of the reasons it's good for waveguides is because of its symmetric nature, you tend to have minimum things like polarization dependence. It's got a high refractive index, so there's good confinement. And of course, the other thing about silicon is that it's got a high quality native oxide, right? And it's abundant, right? Literally, I can almost go to the beach, you know, fill my pail up with, you know, with sand, and then go through, you know, a lot of refining processes, right? Including fractional distillation. I basically convert my silicon, you know, oxide into silicon. I convert that into a liquid. I do fractional distillation, and then I turn it back into silicon, right? You know, but I can make very high purity material from, you know, very abundant, an abundant supply. Now, you know, that's qualified a little bit. I mean, you know, as it ends up, there's better places than others to get your SiO2, but it's abundant. You know, it's not like other materials, the 3,5s, for example, where there's a more limited amount. You know, there's a finite amount of gallium, right? So what's wrong with silicon? Okay, well, first of all, it has an indirect band gap, right? For doing anything involving photons, indirect band gaps are undesirable because you've got the momentum problem. Compared to other materials, it's got a little bit lower electron and hole mobility, so it's slower, right? You know, silicon is silicon. You can't necessarily make complex lattice match other interfaces. The thing that makes it a good waveguide, that high symmetry, makes it a lousy electro-optic material, right? It has virtually no electro-optic effect, and the only way that we can make things like modulators is by basically creating a p-n junction and changing, you know, the carrier concentration in order to change refractive index. Okay. To make waveguides, you have the advantage of silicon on insulator, right? So basically, I can make SOI wafers. Those silicon insulator wafers have a thin silicon layer, they have an oxide layer, and they have silicon. That oxide gives me, again, a good waveguide. But the problem is that oxide is a lousy thermal conductor. Okay, so anything I put on top of that is going to be in a challenged thermal environment. Okay, and I've got a couple slides later to talk about that. And then, you know, it is a material that if I start talking about wanting to run things at high temperature, we're somewhat limited. Because of its band gap, if I start increasing my temperature, I get a lot of free carriers, and those things degrade the performance of my circuits and devices. So it's not like a material like gallium nitride, which naturally operates better at high temperature because of its wider band gap. Silicon is limited. There's a lot of things that are coming about that we'd like to be able to augment silicon for. You know, so of course, you know, everyone knows that we've got a very large number of optical links in data centers. Many of those links use multi-mode fiber and VCSELs. Those are limited, however. You know, if I have a VCSEL-based link, even with high bandwidth multi-mode fiber, I'm limited in terms of how long that link can go by the modal bandwidth of my fiber and also the speed of my VCSEL. So even though I can cover a lot of applications inside data centers with those, I can't cover all of them. You know, and inside a data center, you might be routing something for over a kilometer if you're going from one side to the other and you've got one of your longer links, which means that things like single mode fiber begin looking interesting, and sending large signal, a large amount of data over single mode fiber requires you to have coherent communication, and that's again an area where you know, we're building up coherent receivers, especially coherent transmitters as well. The transmitters are easier, is an attractive area for silicon photonics. For automotive applications, people have been talking about LiDAR for self-driving cars. And we'll just, for general automotive applications in general. And then a number of people also have been looking at ways of augmenting the speed of silicon by having CMOS and then something like perhaps a high-speed indium phosphide HBT integrated with that in order to allow you to do things beyond the conventional limits of silicon, so like 5G, 6G, things like that. So there's a lot of these emerging applications, largely driven by either one, the desire to do things of a photonic nature, right? Or two, have speed, that you can't get with your silicon devices. A handful of years back, DARPA had a program where they were trying to really push heterogeneous integration forward. It started as DAHI, and it had a very variety of names. Dan Green was the guy at DARPA who was pushing that at the time. And he was basically saying, well, here's a number of things that we might be able to do if we had the capability of putting other sorts of materials, onto silicon. Now, he was focused here mostly on the electronic applications, so basically saying, well, if I want to do a low noise amplifier, ideally what I'd like to have is either indium phosphide HBTs or gallium nitride, but I'd like to do all of my control and reconfigurability in silicon CMOS, Or if I want to do something like, have, filtering, it'd be great if I had RF MEMS with silicon CMOS, or tunable filters, indium phosphide HBTs with silicon CMOS. So you can see the theme here where you're adding a unique functionality that the 3.5s do well, but you're augmenting that with the power of CMOS for programmability, control, things like that. Okay. So that's electronic. From a photonic perspective, there's tremendous interest in increasing the data rate, both for long haul links, but also within data centers itself, and what's the limit? Well, I mean, it's interesting because I remember people arguing maybe a couple of decades ago, why do I need to have 10 gigabits over my fiber? I mean, with 10 gigabits per second, you can pass, the entire Library of Congress in whatever the amount of time is, And those arguments were taking place. Basically, people were saying, we don't need the speed, right? And other people were saying, no, I mean, if we have the speed, people are going to figure out ways, to use it, right? High speed video streaming, virtual reality goggles, whatever you want to say, right? All those things to do them well require speed, and even, in a self-driving car. I mean, if every car, to make self-driving cars safe, what you really need to have is every car is sensing everything, and all those sensors streaming their data to a central system that then looks at what's happening with all the cars, right? So you look at that, no matter what we figure out, there will always be a need for more speed, right? And that's been basically manifesting itself by, driving from, things like simple directly modulated devices to externally modulated devices to coherent devices where we're encoding information, not just in amplitude, but in phase, So all those things push the need for higher speed. Okay. So let's spend a little more time talking about heterogeneous integration itself. So a lot of this motivating, why do we want heterogeneous integration? But let's maybe spend a little more time focusing on what some of the problems are and methods that people have looked at over time to achieve the integration of non-silicon materials on silicon, okay? So I like to put this up because it really I mean, and the guy that did this, Wotan Abir, I mean, he does nothing else in his life except produce this diagram. He's done, you know, a lot, you know, I mean, because, and that's not commenting on him or his work or anything, it's just saying this is really good because it basically summarizes what the problem is with heterogeneous integration that we're trying to overcome. Quite often what you'll see is something that shows lattice constant versus band gap, right? Well, that's important if I'm designing a device, right? If I want to make a heterostructure device, I need to stay with the same lattice constant, and I want to build up a structure. But this more importantly shows what can I realize without messing my material up, right? And the two most important things are how much deviation does my lattice constant have from the material I'm trying to put it on? And secondly, what is the thermal expansion difference? Okay, I mean, if I have two materials that are perfectly lattice matched, but they have a huge difference in thermal expansion coefficient, I'm gonna have a reliability problem. So this encapsulates both thermal expansion mismatch problems as well as lattice mismatch problems, okay? And if I look at silicon sitting here by itself, that really shows you what the problem is, right? The problem with putting materials on silicon is that its lattice constant and thermal expansion coefficient, you know, are both really not well suited to other materials. Now there's things that are, you know, for example, from a lattice constant mismatch, you know, gallium phosphide has, minimal lattice constant mismatch, but it's got big thermal expansion coefficient mismatch, right? So that really highlights the issues. Now there's certain magical systems that end up being useful. Sorry, I guess I didn't build. There are certain systems that end up being magical for various reasons. Gallium arsenide and germanium. Anyone know what gallium arsenide and germanium is useful for? So, that's okay. I mean, if I'm throwing a satellite up, right, I want to throw a multi-junction solar cell on there because if I'm up in space, the amount of power that I get out of my solar cell is absolutely critical, right? On Earth, you know, I've got millions of miles of cornfield. I can, you know, stick crummy solar cells on my cornfields, right? Well, I mean, limitations to that as well. But if I'm in space, I need to have the highest efficiency cell possible. And as it ends up, gallium arsenide on germanium, and then indium phosphide on top of that, is great at harvesting a greater amount of the solar spectrum so you can get more power, more efficiency. The most efficient solar cells made, or some of the most efficient ones have been made on, you know, on that system. Okay. Down here we've got silicon carbide, and fairly close to silicon carbide we've got our gallium nitride, aluminum gallium nitride, some other materials. You know, that's proven to be interesting. You know, silicon, of course, is way over here. You know, there's, you know, some other materials that have, you know, that have come in, indium phosphide, indium arsenide, aluminum gallium arsenide, gallium arsenide. All those things, you know, are in parts of this where we have good match between lattice constant thermal expansion coefficient. It's sort of interesting over here, people have been playing around with this system, boron nitride on diamond. I don't know if anything will come of that at all, but, you know, but it is one that's sort of interesting from the standpoint of this, you know, this metric, okay? Now, people have recognized almost from the early days of compound semiconductors that it would be really nice if we could stick them on silicon, right? In fact, if we go back to the 1980s, you know, back to when a lot of the growth technologies we use today, MOCVD, MBE, were really, being worked on very aggressively. People tried doing direct growth of 3-5 materials on silicon. In fact, back when I was in Nick Holoniak's lab in 80 whatever, we had people working on gallium arsenide based lasers on silicon, okay? And you could make a gallium arsenide based laser on silicon. The problem was it lasted for about 30 seconds, okay? And the reason it lasted for 30 seconds or less was because of the issue with defects, right? In order to make a lattice mismatch material, I'm gonna have to put a big buffer on there to try to get rid of the defects that I'm producing as a consequence of lattice mismatched growth. Even if I do tricks, if I do tricks like having super lattices or have, in the growth process, you can vary temperature to try to bend your dislocations over, I still have this huge dislocation network sitting below my device. And eventually, when that dislocation grows due to heat and light driving the defect into my active region, it's going to explode and my device is going to die relatively rapidly, okay? Regardless of what I try. Pseudomorphic growth, superlattice buffers, growth on pattern substrates, light and heat drive dislocations. So this was a focus for a long time, but ultimately, it had problems. Now there is, I'm going to mention something in a moment that did overcome some of this issue, but fundamentally it's still there. Those defects are present. Getting more into like the late 80s, early 90s, people said, well, silicon is this great platform. Let's use a silicon optical bench. So a silicon optical bench basically says I've got a nice flat plane. I can flip my devices onto that using precision alignment, put lasers, modulators, detectors, V-grooves for waveguide, integrated lenses, and I can use those to make little mini optical subassemblies. And people still do that today. But it's really, this is not something that is scalable in the same way that silicon is, right? If I'm doing precision placements of lasers, every precision placement takes a certain amount of time, minutes typically, and if I'm trying to do this at a very high, high volume scale, I'm going to be limited by the need to do those precision placements. So it's a solution, but not a great one. Okay. Another thing that came in the 90s was wafer bonding. Does anyone know where they see wafer bonded devices every day when they're driving, presuming you're driving, or if you're driving, from wherever you are to campus? Red stoplights. Okay. So at that time, Hewlett Packard, they began bonding indium aluminum gallium phosphide LEDs onto transparent substrates. So they'd grow on gallium arsenide, right? Because indium aluminum gallium phosphide is lattice matched to gallium arsenide. But the problem with gallium arsenide is its band gap, right? It's going to absorb the photons that are generated by my red LEDs. So if I leave it on gallium arsenide, I lose half my photons, because again, they're going off into 4 pi steradians. I've got, an island of opaque material below. I lose those photons, okay? So by putting things on transparent substrates, I have the capability of harvesting photons that I previously would throw away just due to absorption, okay? And that became an important technology. Smart cut became an important technology. So people wanted to have SOI wafers, silicon on insulator, for making higher speed electronic devices. And it was discovered that you could use a technique called ion slicing. I basically take and implant a wafer with a very specific energy that creates a peak of a material, let's say helium or hydrogen. If I heat that up, I form little micro bubbles. I basically create a micro cleave, and I'm able, if I bond that onto another wafer, to basically create an SOI wafer using this ion slicing technique. That's been used for a number of different things. People have demonstrated for 3-5s, magnetic materials, niobate people have done it with, but it's mostly used these days for silicon insulator. And if we progress, more now into the 2000s, a number of interesting developments occurred. People started doing quantum dot devices. Now, quantum dots are sort of interesting. And one of the groups that was working on this for lasers on silicon was doing basically indium arsenide dots on silicon. The nice thing about a dot is that if your defect crawls up into the active region, you kill a more limited portion of your active region, right? You might wipe out one of your dot or a couple of your dots, but your defects don't grow in the same way. So you can get better reliability on quantum dot lasers on silicon than on other quantum well lasers on silicon, but they're still not perfect. Low temperature wafer bonding started coming in, so low temperature wafer bonding, people were using things like plasma activation of surfaces followed by wafer bonding, that works well with oxide surfaces, and some other techniques, van der Waals plus chemical bonding, and a number of other things, to basically allow bonding to occur at lower temperatures than could previously be done. And kind of getting a little bit later, people were doing things like direct bonding of 3-5s, onto silicon, to make heterogeneous lasers, BCD bonding, metal bonding, growth on embedded templates, things like that. So basically there's been a progression, and people today are talking a lot about heterogeneous integration because this kind of progression has allowed problems to be solved and methods to be developed that enable these applications, to work with devices that are potentially more reliable. There's still more work that has to be done. So what I'm going to do now is just kind of walk through a couple things that have happened over time. In kind of more, more recent years. So in silicon technology, to push things to higher speed, people have been working with things like growth of indium gallium arsenide devices on silicon using thick buffers. These are more for electronic applications. There's been work using growth on buried layers. So an example here, you have a silicon substrate. You have something that they call the compound semiconductor template, which in this case is germanium. We know how to grow gallium arsenide on germanium, and we know how to grow indium phosphide on gallium arsenide. Again, there's defects involved, but you can basically do a multi-step growth process in order to get that. And then this is also showing another kind of interesting thing where with this silicon substrate, this might not be a device quality substrate, but you can wafer bond something like 100 higher quality CMOS layer on top of that, and utilize that to make your CMOS devices, and then you've got your 3-5 device that you've grown, on this template layer. And people have demonstrated pretty interesting electronic results with this. I mean, in this particular instance, They were growing indium phosphide HBTs that had an F max greater than 200 gigahertz, and we're integrating that with CMOS circuitry. Same is true of gallium nitride. This is sort of interesting work here. Here they basically grew gallium nitride on 111 silicon, which people can do at wafer scale. And then they put an oxide layer on here, wafer bonded a 100 silicon layer, and using ion slicing, similar to the technique that's used for making SOI, they produced a thin layer of that, and they made their CMOS circuitry on that. So they were able to integrate gallium nitride-based devices with basically silicon CMOS devices. This is some other interesting work. This came actually out of the University of Michigan. Here what they were doing was growing nanowires of gallium nitride, basically 3 nitride devices on silicon, and making lasers, detectors, and waveguides using this nanowire material. Now, these devices weren't great. In fact, not great means, well, I'm not going to say lousy, but the threshold currents were high. There were various problems with them, but it basically showed promise as a technique for integrating those materials onto silicon, again in a wafer scale process. And I mentioned the indium arsenide quantum dot work, and this is again another interesting demonstration where they were able to make, in this case, not bad lasers with reliability that was reasonable, using structures that had defects, but because of the quantum dot, if the defect intercepted the active region, it would not cause the same kind of lethal damage that you'd see if you had a quantum well device. Okay. That's a little bit on direct growth methods. With regard to bonding approaches for heterogeneous integration, you've seen a number of groups doing things involving BCB bonding. BCB is basically a polymeric type material. This has the advantage of being scalable, but it does have the disadvantage of not giving you a really great thermal environment for your device, because BCB is not a really good, does not have a great thermal conductivity. The folks at Ghent made 3-5 lasers on silicon using BCB bonding. So they basically took a 3-5 layer, they patterned that and etched it such that there was a taper. In the gain region, you'd have propagation of your 3-5 material. At the edges of that, they would couple into a silicon waveguide, and they were able to make lasers on silicon using this approach, but again, the lasers were not great, higher thresholds and not really good thermal performance. And part of that was because of the thermal environment created by that BCB. Okay. Plasma-assisted wafer bonding has been also used, so this is what Bowers did. This figure probably showed up in 1 million publications. But basically what they did was took a gain region, a 3-5 gain region, using plasma activated low temperature bonding. They bonded that to a silicon waveguide, such that the mode was mostly present in the silicon waveguide, but had enough overlap with the gain region to allow the device to lase, and they were able to make lasers using this technique as well. But again, you know, there's some limitations to that. The first one is the threshold currents aren't high. If you think about this, I have a lossy interface in my laser cavity, right? Because again, if I'm doing low temperature wafer bonding, I'm going to have a defected interface. That defected interface is going to give me mid-gap states. Those are going to absorb my light. So inside my laser cavity, I have an absorber, right? And that's undesirable. But, you know, again, it represents an interesting approach. And then prior to coming to Illinois, I was involved with a group that was doing direct bonding of 3,5 material to the silicon, creating basically bridge waveguides between the gain media and the silicon waveguides, so that you were able to make tunable lasers using an integrated gain material, where now instead of coupling across an interface, it's edge coupling. So there's still a little bit of optical loss here and a little bit of optical loss there associated with bridging between the 3,5 and the silicon, but it's not going the entire length of the device. Okay, so the loss is lower. And that was the basis for a company that's still out there making silicon photonic devices. And of course, you know, with wafer bonding in general, very large scale systems are available for doing that. This is an example of an EVG cluster tool that's used for commercial wafer bonding. This is, in fact, we tried to get one of these in Illinois. The problem is it cost about $10 million when all is said and done. But you know, the key thing with these tools is that by the combination of oxide removal using a plasma process and then bonding at a slightly higher temperature, you're able to produce pretty good interfaces between a 3,5 material, you know, and other materials like silicon. Well, this is gallium arsenide phosphide, and people have also done it for silicon and other materials as well. But it is still not a perfect interface, right? I mean, you know, this is going to have slightly different optical loss characteristics and also electrical characteristics that, you know, that may not be perfect. In fact, when people are doing this process, a lot of what they work on in optimizing their parameters is trying to improve both the electrical properties of the interface and optical properties. There's some other interesting, and this is just to kind of fill out things that are out there that might be tools that become useful for doing heterogeneous integration. One of those is metal film bonding. You know, so with certain materials, if I have a flat enough surface, if I bring my metals together, for example, if I bring gold together with gold, and that material is flat enough, I can basically create a bond by just pushing my materials together, okay? With other materials, I might need to do this in a vacuum environment, or I might need to do it in a place where I can remove the metal oxide layer. But if you look at systems that people who have demonstrated this in, they've done it with titanium, silver, platinum, chrome, moly, tungsten, you know, so all of these have been used to form these metal bonds, which are high quality, but they have limitations with regard to the sort of apparatus that you need in order to do this, because you need to be able to do it in vacuum, you need to be able to clean your surface, you need to be able to flip, you need to be able to align and bond. So again, doing something like this requires the same sort of cluster tool that we saw in the previous slide. You know, another interesting thing that people have done has been using exothermic processes. So here, with certain types of materials, for example, nickel aluminum, aluminum monel, nickel silicon, aluminum zirconium. If I create effectively a super lattice of that material on two different wafers and I bring it together and I nucleate a reaction, I'll create a bond by using that process, because as it ends up, it's an exothermic reaction. So the reaction, once it starts, will propagate, okay? But the issue is, you know, first of all, I need to nucleate that. And typically the ignition might be something like a spark, you know, or a thermal event, maybe a laser pulse or something to basically get that process nucleated. But, you know, again, as with anything else, you have, you're not, whenever you have a reaction like that occurring, you're not perfectly in control of what happens on both sides of that. So you have to worry about things like, what is this going to do to my layers above and my layers below as a consequence of this exothermic process going on between them. Now, some people have used, for example, nickel silicon. So that's a material that does have this exothermic process. But if you put, for example, a nickel layer, you know, on indium phosphide in-gas structure, and you form that nickel silicon bond, which occurs at temperatures around 400 degrees C or so, you can use that to create nickel silicon, or to create indium phosphide fins on silicon, and that can be used, or has been used, to basically make in-gas fin feds. Okay, so. And then there's another, you know, kind of interesting type of system that people have used, and that's basically bonding using a paratectic alloy. So for example, indium palladium is one system that has the capability of melting at a low temperature, okay? And then, you know, if, for example, I have liquid indium in contact with the palladium layer, what's going to happen is there's going to be reaction between those, and I'm going to form palladium-3, indium-7, and that, as opposed to having a melting temperature at the temperature of the indium, is going to have a melting temperature close to about over 600 degrees, almost 700 degrees. So basically, I can take something, bond at a low temperature if my layers are thin enough, and then if I fully consume my indium and my palladium, that bond is going to be stable up to, you know, almost 700 degrees. And, you know, again, with regard to other things people have done chiplet transfer. One of the questions or criticisms of 3-5 bonding onto silicon was wafer size mismatch, right? So basically, most of my 3-5 wafers, maybe I've got a 6-inch wafer, you know, gallium arsenide. Now there's some 8-inch wafers available. If I've got a 300 millimeter silicon wafer and I've got a, you know, a 6-inch gallium arsenide wafer, how do I distribute that gallium arsenide onto my silicon? Well, one of the things people have done, you know, has been to basically dice the wafer up, put it on something like a wafer tape and stretch it out, and then basically bond one onto the other. This is not a perfect solution. People have also done things like smart cut with 3-5s as well. So, you know, we're running out of time. I do want to talk about one thing that we're doing in Illinois, which solves the problem of wafer size mismatch without the variability associated with trying to use something like wafer tape to stretch your wafer. You know, so in this method, we imagine that we've got a silicon wafer going through the front end of line process of our silicon fab, and we have a second silicon carrier wafer, and then we've got our 3-5 wafer. So we basically take that silicon carrier wafer, after dicing our 3-5 material, we mount that epi side down on our silicon carrier wafer. We then remove our substrate, do photolithography so we can precisely define where those 3-5 islands are, and then do a single wafer bonding process where we bring these two together. Okay. And if we kind of imagine what that looks like on a cross-sectional basis, we have our silicon carrier wafer. This is our 3-5 epi side down. We basically remove the substrate. We do dry etching to precisely pattern where the 3-5 material is located. We then deposit a bonding material onto that. So this is a temporary bond, by the way. We carry that through, we flip it over. On our silicon host wafer, we have receptor sites that we've metallized using a different metal. And then we do a permanent bond between those, release our temporary bond, and we end up with 3-5 islands precisely located on our silicon host wafer using this epitaxial transfer process. Now there's some particulars to that. The first one is, what sort of metal scheme you use. Well, as it ends up, aluminum and germanium have a very nice eutectic temperature, so I can form a permanent bond using aluminum germanium 400 degree-ish or so, maybe as high as 450, but ballpark in the 400s to basically form that permanent bond. And also, beneficially, that acts as an ohmic contact to my gallium arsenide. Okay. This is just kind of showing, of course, we're doing this on slightly smaller wafers here, but you can use things like a 3D printed template to basically coarsely place your pieces. And the reason we're doing, by the way, this is to eliminate the need to have every single photonic device be precisely placed, with micron scale precision on the wafer. By using a carrier wafer like this, we can coarsely place all of our 3-5s and then photolithographically define where it is on our carrier wafer. So basically, instead of doing a million alignments for every photonic device we have, on that 300 millimeter wafer, we do one alignment process. Yeah, and we've done that with laser material. This is kind of walking through some process steps, kind of showing what our chiplets look like, and we've used this to kind of bouncing through things here. We've used that to fabricate both light-emitting transistors after the transfer process, and also, more interestingly, VCSELs. So in this work, the VCSELs were formed on the host wafer after the transfer process. So basically now all of our apertures can be defined relative to features existing on that silicon host wafer with photolithographic precision. All the processing is done afterwards. Okay. And I know we're running out of time, so I'll mention just a couple things in these slides. The first one is the thermal problem associated with oxide layers. This is reinforcing a point that I was making earlier with regard to the problems with either BCB bonded devices or the heterogeneous devices that were bonded in the kind of UCSB approach. If you're not directly on your silicon substrate, you can see significant temperature rise in your devices. And if you look at things like your Li characteristics for the various approaches people have used, you see over temperature the impact that either the BCB bonding or the direct bonding onto something that still has a box layer has on the device. It basically loses its performance at an elevated temperature. and, you know, I'd be remiss if I didn't mention a couple things that, you know, that everyone was talking about 10 years ago and nobody's talking about today because nothing happened. You know, the first one is, you know, strained germanium tin, lasers. You know, so this is basically putting lasers on silicon using strained materials, strained germanium. Everyone was saying, oh, this is going to revolutionize the world, and, you know, of course it didn't. Interesting work, interesting results. I mean, to keep in mind in the background with regard to things that can be done, because again, the reason this works is because the direct and indirect values in germanium are pretty close to each other, and if I strain them, I can push it over such that it acts direct, but I still have an indirect value sitting really close. And, you know, again, in silicon photonics, we've got a number of devices. I'm going to skip over all this. This is just in there for, in case people were interested. You know, and you know, where we're going as we push forward is integration with wider bandgap materials. Nitride photonics, you know, might be something that's interesting that develops because it allows us to do shorter wavelength lasers than we can currently do using materials like silicon, because with nitrides, we're in a portion of the spectrum that's transmissive. That might be important for things like quantum applications. So, just to wrap up, I mean, you know, obviously, heterogeneous integration, as I said before, is an overnight success. You know, 20 years in the making. Today, it's being driven by real demands, the real need for things, you know, to basically enhance the performance of our silicon. You know, and you know, again, looking forward, you know, I think that we're going to continue to see more use of 3.5 materials, integration of 3.5 materials onto a silicon platform in order to achieve some of these application needs that we see. So with that, you know, again, thanks very much, and again, happy to.
Real quickly, are there any burning questions from the audience? Because if not, I believe Professor Dallesasse will be able to stick around during pizza, which I'm sure everyone is excited for. Feel free to ask some questions then. Okay, awesome. If people want to start